Good day, students. You are welcome to your favorite YouTube channel, Physics for Everybody. Today we'll be solving the Physics IGCSE October-November 2022 paper 6. Okay, and we're focusing on variant 1 of paper 6. The duration of this exam is 1 hour. So we try to limit the duration of this video to 1 hour, but because of the explanation, the duration might extend to 2 hours or 1 hour 30 minutes. Let's go to question 1. A student investigates the period of a pendulum. Figure 1.1 and figure 1.2 show the setup. So this is the pendulum bob, and this is what happens when the pendulum bob begins to oscillate. Take note of this arrow here that indicates that for you to have one complete oscillation, the pendulum bob has to swing this way and then swing this way to the extreme end and back here. This is one oscillation. Now, the question: explain briefly how to measure the center of the pendulum bob as accurately as possible. So if you want to measure to the center, so you want to measure the length, okay, that's this measurement taken here, and get into the very center, the middle of the pendulum bob. How you do that? You just use a meter rule and you ensure the meter rule touches the center of the pendulum bob. Okay, so you just place a meter rule beside your pendulum bob and you ensure the meter rule touches the center of your pendulum bob. So you place your meter rule can look like this. Yeah, your meter roll is meant to be straight, right? Good, so your meter roll should look like this. Something like this will work, okay? And this will be the marks on the meter roll. So something like this will enable you to get the length to the very center of the meter roll, okay? Good, so you write that down here. You write that down here. So you write out your answer like this by placing the meter roll beside the pendulum bob and ensuring the meter roll touches the bulb. So there's another way of getting this done. You may attach a horizontal aid to a meter roll, and the horizontal aid will be able to slide in both directions, both upwards and downwards. This horizontal aid, in this case, we are using a set square, okay, and the meter roll. Now, when you want to read this instrument, this combination, whichever mark that so you see, whichever mark on the meter, on the horizontal aid that is in line with any mark on this meter roll, that is the mark you pick, the reading you pick. For instance, in this case, I will be picking this horizontal aid. Along this horizontal aid, any part of the meter roll that is in line with this line, this will be the reading. So this is the length in this case, okay? So if I want to pick the length of this pendulum bob, I will just slide the horizontal aid downwards further till the horizontal aid is here, and then I'll pick this length as the length of the pendulum bob. Let's go to the next one. So the next question says, the students adjust the length of the pendulum until the distance L measured from the bottom of the clamp supporting the pendulum to the center of the bulb is 50 centimeters. Okay, this is our first length, 50 centimeters. He displaces the bulb slightly and releases it, so it swings. Figure 1.2 shows one complete oscillation of the pendulum. He measures and records the time t for 20 complete oscillations. Calculate and record in table 1.1 the period t of the pendulum. The period is the time for one complete oscillation. Calculate and record in table 1.1 the value of t squared. So let's start by calculating the value of one complete oscillation. The question asks you to calculate, calculate and record the period. You are looking for period, and you are also given the definition of period. That period is the time for one complete oscillation, right? Good. That means now period is the time for one complete oscillation. You were told that the students record the time for 20 complete oscillation. Now, this is the time for 20 complete oscillation. How will you now get the time for one complete oscillation? Period is time for one oscillation. So period is the time divided by number of oscillations. What's the time here? The time here is 28.2. So we have 28.2 divide 28.2 divided by the number of oscillation. You know there were 20 complete oscillations. So divide it by 20. 28.2 divided by 20 will give us 1.41. Yeah, so 1.41. That's the period. And the next thing you record is period squared, t squared. So if t is 1.41, what is t squared? Then you do 1.41 squared. Let me fix this. So now you do 1.41 squared. So you open your calculator and you type 1.41 squared. Let me confirm this. 28.2 divided by 20, we get 1.41. Okay, good. So that 1.41, you have to multiply it by 1.41. 1.41. Yeah, that's 1.41 squared. We got 1.988. That's 1.99. Yeah, 1.99. So you write it here. 1.99. Do I'm writing this is not good enough, so I'm going to zoom in so I can write appropriately. 1.99. 1.99. Good. So that is settled. Let's go to the next one. Let me just confirm what I wrote. 1.99. That's good. So the next question says, let me erase all of these things that we do not need so it does not cause confusion. The question says, he repeats the procedure using L values 60 centimeter, 70 centimeter, 80 centimeter, 90 centimeters, and 90 centimeters. The readings and results are shown in table 1.1. So this is our table 1.1 and these are the readings and the results. Okay, you have t squared, you have length, you have length, you have the time, you have the period in second, and you have the period square in second square. Okay, length in centimeter, time in second. Okay, so let's go on with the next part of the question. The question says, plot a graph of t squared. Okay, it's a graph of period squared in second square. That will be on the y-axis against length in centimeter on the x-axis. Start the t squared axis at a convenient value close to the minimum value of t squared. You know we have t squared on the vertical axis and values of t squared range from 1.99 to 3.65. And you are asked to start it on a what? At a convenient value. That means it's not compulsory you start the origin from 0. You can start the origin at a value as close as possible to the 1.99. That is understood, right? Good. That is understood. So what value is close enough to 1.99? So you are going from 1.99 to 3.65. Let's see. If we start our values this way, if we start with, let's say we start with 2 here, 2.5, this will be 3, this will be 3.5. Yes, that's fine. That's fine. This will be 4. Okay. So instead of starting from 2, let's start from 1.5. Okay. So since t is on the vertical axis, we start picking our value of t from 1. Let's see, 1.99 to 3.65. So our value on the vertical axis will range from 1.99 to 3.65, and our values on the horizontal axis will range from you are plotting a graph of t squared against L. These are the values that will be on the horizontal axis. So our values on the horizontal axis will range from 50 to 90. So our values on the horizontal axis will range from 50 to 90. Now I will zoom in so I can pick appropriate values for what we have on the vertical axis. So this will be easier when you are doing this on your graph book in the classroom, in the examination hall. So let's go. So we let our smallest value be 1.5. So the next value will be 2.0. The next value will be 2.5. The next value will be 3.0, and the last value on the vertical axis will be 3. No, this is not the last value. We have 3.5. Okay, then the last value will be 4.0. You can stop it at 4.0. Yeah, 4.0. So we have to draw the axis. Okay, the axis must be shown. That's what makes it a graph. So you have to use your pencil and a very straight ruler to roll this vertical axis. Okay, so I'll roll the vertical axis now. Now you have to draw this vertical line indicating the y axis. So I have to draw this vertical line. You use your pen and ruler. Ensure you use your pen and your pencil and ruler, please. While doing this, you must use your ruler. This is very important to use your ruler. So you draw this vertical line, which is your y-axis at this edge, and you name it your y-axis. Okay, you have to put your arrow here, and then you put it your y-axis. What are you plotting on your y-axis? Time squared in second, period square rather. Okay, not time squared, period squared, t squared in second square. So you write here t squared in second square. You do likewise for the horizontal axis. Okay, now we are done with the vertical axis. We can erase this. We only use this to guide the process of what we were doing. Now let's go to the horizontal axis. Looking at the horizontal axis, our values range from 50 to 90. We also draw the horizontal line. You have to draw this horizontal. Oh, this is not good enough. Ensure you use your pen, your ruler, your pencil, and your ruler while drawing this. This is not good enough. So you draw the horizontal line with your ruler, okay? When you use your ruler, you won't make mistakes like this. And what are you plotting on the horizontal axis? You are plotting length. Let's see. The graph says, the question says, plot a graph of t squared against what? Against L in centimeter. So down here, we put L in centimeter. Good. Also, we need to calibrate this. You know, the calibration will go from 50 to 90. So we calibrate it this way. We have 50, 60, 70, 80, 90. We have 50. Let me zoom in so it can be easy for me to write all of this. This will be my 50 centimeter. This will be 60. This will be 70. This is 80. And this is 90, all in centimeters. Okay, so you have shown the axis and the label, that is length in centimeters and times and period square in second square. All of that gets you your full 1 mark. Now you start picking your values on the graph, okay? When the length was 50 centimeters, let me use this color to highlight this. When the length was 50 centimeters, period was 1.99, which is the first line, okay? So you keep picking them. These are the only two values you need on each line, the first one and the last one, okay? Then you go to the next one, you pick the two values you need. Let me use different colors so that it will be easy to distinguish each of the values you are plotting. So I'm picking this value here, the value here, okay. Then the last value will be plotting. You pick this let's use color pink, this value here and the value here. Okay, the value on the left end is your length, the one at the right end is your what? The one at the right end is your period in second square. That's clear, right? Yes, of course, that is clear. So the first one, I use color red. Let's go and pick length 50 centimeter and period 1.99 seconds squared. So we use your pencil, you are plotting a graph. So you use your pencil, you pick length 50 centimeters, okay? So you draw dotted lines. You use your pencil to draw dotted lines. You trace it to where you have period 1.99. What is period 1.99? You know, on the vertical axis, each division is how many units? Each division will be 0.5 units. Why? Because if you look at the vertical axis, okay, the first division you have is 1.5. I think I've erased that mistakenly. Let me write it back. On the vertical axis, the first division you have is 1.5. Now, from that first division up to the next division, if you take the difference, 2.0 minus 1.5, you get 0.5. Now, because there are 10 divisions between these two, that means each division will be 0.5 divided by 10. That will give you 0.05. That means each division on that axis is 0.05 units. Okay, good, that's 0.05 units. So the first division is 1.5. Okay, the first division here is 1.5. Okay, then we start reading upward after that. The first one is 1.5, which is this one. The next one will be 1.55, 1.6, 1.65, 1.7, 1.75, 1.8, 1.85, 1.9. This is 1.95, 2.0. The closest division to 1.99 is not this. This is 1.95, and 1.95 is now closer to 1.99 than 2.0. So we are using 2.0 as our value for 1.99. You get it? Good. So we are using 2.0. So we come and draw dotted line from 2.0. Where these dotted lines meet, we put a plus sign here. Yeah, because this is a very important point in the graph we are drawing. So just the way we did this, we follow the same pattern in every other thing we are doing. Okay, so let me erase the parts of this that we do not need. All of these are not part of the answer. Okay, so I'm putting back everything we need in this graph. This is 2.0. This is 2.0. That's the division we have here. Good. So we've gotten the first point. Now we're going to do this for every other point. Let's go back to our table so we can get every other point. From our table, when the length is 60, the period is 2.43. So we go to 60, we draw our dotted line and we'll bring it to 2.43. Let's go to 60. So at 60, let me go back to our pencil so I can draw. 60, I will draw dotted lines. I'll bring them up here. Then I'll go to 2.43. This is 2.0. The next division will be 2.05. The next one will be, okay, this is 2.0, 2.05, 2.1, 2.15, 2.2, 2.25, 2.3, 2.35, 2.4. This 2.4, this 2.45. 2.43 will be in between, 2.43 will be here, in between 2.4 and 2.45. Yeah, the first, we have 2.4, and the next division after 2.4 is 2.45. Okay, this 2.4 can be taken as 2.40. So between this 2.40 and 2.45, we will have 2.425. which is approximately 2.43. So 2.43 is taken as this division here between 2.4 and 2.45. So I'll draw my dotted line here. So after tracing the line from 2.43 on the vertical axis and 60 on the horizontal axis, where those two meet, then you put a mark here, a plus sign here, okay? So this point is very important in getting the slope of this graph. Let's go. The next one is, let's go to the table to pick the next point that we need to plot. So from the table, we have, let me remove this. From the table, the next point we have, that's orange color, 70 and 2.82. 70, 2.82. So 70 on the horizontal axis, then you pick 2.82 on the vertical axis. So we trace 70 vertically, no. We trace 70 vertically upwards. Let me zoom in order to reduce mistakes. So 70, we trace it vertically upwards. And we're going to plot it at the same, plot it against 2.82. So how do you get 2.82? It's 2.5. Here is 2.5, 2.6, 2.7, this 2.8. We take this as our 2.82. Yeah. No, 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 no. 2.82. 2.82. Now, this is 2.8. The next one is 2.85. Between 2.8 and 2.85, we have 2.83. Yeah, so we have 2.83. This is 2.83, and we're using this as our value of 2.82. Yeah, 2.82, because it's the closest value, 2.82. That's what we are going to use. So where those two meet, you put a plus sign here, and then you go ahead to pick the next 2 points from the table. So we pick the next 2 points, and that's the blue color, 80, 3.20. 80 against 3.20. So we go to where 80 is, and then we trace it vertically upwards, 80. When you are doing this in the classroom, in the exam hall, make sure you use pencil, please. Very sharp pencil. 80 against 3.20. Sorry. 80 against 3 points. 80 against 3.20. Okay, so where do you have 3.20? If you look at the graph, this is 3.0, 3.1, this 3.2. So these are 3.20. You know, each division is 0.05, and we have 4 divisions between 3.0 and 3.20. So we trace 3.20 to 80. This, I don't know, let me zoom in so I can do a perfect job here. I think this is better. Alright, so we trace it to 2 points. We trace it to where we have 80. When you're doing this is an example, make sure you use your pencil, your ruler, so you get perfectly straight line. So where they meet, you put a plus sign there. So this is good. Then the next values we have will be 90 against what? Let's see what we have there. we have 90 against, oh, that's the last value, 90 against 3.65, 90 against 3.65. So you go down here, yeah, let's have it here, 90 against 3.65. Oh, 90 against 3.65. So this 3.5, 3.55, 3.6, 3.65 will be here. Do not forget that each division is 0.05 units. So where they meet, we put a plus sign here. Good. So all of these have been done. Let me erase every other thing I do not need here. So let me erase every other thing I do not need, so it does not cause any form of this of interference with the real solution. Now, if you look at this, you see we have all our points arranged along a straight line. Now we place a very long meter rule above these points, and we draw a very long, a long regression line. It's called the regression line. We place a long meter rule, and then we draw a straight line that passes through all these points. Ensure you use your meter rule to draw this straight line. Does this look straight? This doesn't look straight enough. I think I could have done better, right? Let's see if I can do better. Let's see if I can do better than this. Okay, let's see if I can do better than this. I want to do another straight line. This is not better. This is worse. Let me make one more attempt, okay? If I can get something better, then we use the better one. Does this look better? Let's use the first line we have. So now we have our, anyway, we have our state regression line. When you are doing this in the laboratory, ensure you use all your drawing instruments. Now the question D, determine the gradient G of the graph. Show clearly on the graph how you obtained necessary information. Now you want to get our gradient. How will you get your gradient? By drawing a big right angled triangle, okay? Then we pick our point and then we calculate our slope. Let us draw a big right angled triangle, okay? Yeah, so how do you draw a big right angle triangle? When you are doing this, make sure you use your pencil, okay? But in order to make this easier for you to visualize, I want to use color blue, okay? But in the exam hall, use pencil throughout for everything you are doing. Don't use your blue color biro, use your black pencil. So I want to draw a big right angle triangle, okay, so I can pick my values. Yeah, so um, let me see. So you can decide to draw your right angle triangle from here and stop it here. You may decide to stop it here, okay? You decide to stop it here, then you draw the horizontal part like this. Oh. You may decide to draw yours this way, a big right angle triangle. Yeah, then you close it, okay? Also, you may decide to just take it to the end. This is not good enough. This is not good enough. Okay, so you may decide to take it to the end. Yeah, so you decide to take it to the end. Yeah, and then you bring it down. So you'll be picking your values from this big right angle triangle. Alright, so we'll be getting our values of dy dx, okay? Do not forget that the slope is always gotten with dy dx, okay? So you pick our y2, y1, x2, and our x1. Good. So let's do our dy dx. Determine the gradient. The gradient is dy dx. How do you get the gradient? Um, Let me put the gradient here, okay, because we don't have enough space there. Gradient, gradient is y2 minus y1 over x2 minus x1, right? Do not forget on the vertical axis we have time, okay, and on the horizontal axis we have length. So our gradient will be t2, okay, minus t1 over L2 minus L1. Why? Because it is L2 and L1 we have on the horizontal axis and T squared on the vertical axis. So that the value on the vertical axis will now be T2 squared minus T1 squared. Okay, because it is T squared. It is T squared you plotted against what? Against L. That's why we are using T2 squared and L on the horizontal axis. If it was a graph of T against L, then we'll be using T squared minus T2 minus T1 over L2 minus L1. I hope you understand how we got those values. I have mistakenly erased the horizontal line here, so I have to put it back here. Alright, so the graph is perfect now. Now let's go. What's our value of our T2? You pick the value of your T2 and the value of your T1. Now let us pick our values on the graph. What is the value of T2 squared? Okay, along the y-axis, what value do you have here? This is 3.5, 3.55, 3.6, this is 3.65. So we'll have 3.65. You are not going to square it. Why? Because the value, the axis, this is the t squared axis. So the value has already been squared from your table. Remember, let me just erase every part of this graph that we do not need. So the value has already been squared from your table of values, okay? So we have 3.65 minus, what value do you have? From the T1, the value here from this point will be our T1. And what value do you have here? 2.0. So we are subtracting 2.0 and we divide whichever answer we get by what's our L2? Oh, sorry, this is a mistake. Okay, I made a mistake down here. This is L1, not L2. Okay, you are doing L2 minus L1. L1. Okay, so what's our L2? Let's go to our horizontal axis, okay? The T2 you picked here corresponds to L at this point. That means our L2 is 90. So you come here, we put 90 minus our L1 is value of L here, which is 50, minus 50. Now let's go. 3.65 minus 2, that will give us 1.65. And the denominator is 90 minus 50, which gives us 40. So 1.65 minus 40 will give us what? 1.65 divided by 40 rather, not minus 40. 1.65 divided by 40, let's do that here. 1.65 divided by 40, and we are having that as, oh, my fast laptop. 1.65 divided by 40 gives us 0.04. and that is the slope. That's the gradient of your graph, 0.04. 0.04. Do not forget that this is a graph of t squared on the vertical axis and L on the horizontal axis. Okay, this is a graph of t squared on the vertical axis and L on the horizontal axis. So then that means if you want to write your answer, you write your answer as 0.04. Since it's t squared on the vertical axis and the SI units of the vertical axis is second square. Okay, t squared is measured in second square. So it starts with the SI unit of what you have on this vertical axis, second squared. Then is a graph of t squared against length. Is the length that you have on the denominator. That will be second square per centimeter. 0.04 second square per centimeters. That is our answer, and that is correct. Okay. Go on to the next question. Explain briefly why timing 20 oscillation gives a more accurate result for the period than timing 1 oscillation. Well, when you are taking 20 oscillation, then any form of error that's coming due to any form of delay would have insignificant effect. It will have very less effect in comparison with when you are taking only one value. Okay, so reading 20 oscillation, it reduces the effect of errors on your values. So I type that here. So taking 20 oscillations reduces the effects of errors on the readings. Okay, be it parallax error, be it zero error, be it human error, it reduces the contribution of errors in your readings. We go straight to question number 2, which is electricity. Alright, straight to question 2. A student investigates the resistance of a lamp. She uses the circuit shown in figure 2.1. This is the circuit. On figure 2.1, draw a voltmeter connected to measure the potential difference PD across the lamp. So this is the easiest among the questions. To draw a voltmeter that is used to measure the potential difference across the lamp, you just draw the symbol of the voltmeter. You make sure, okay, so let me zoom in so I can draw a perfect drawing of this. So I'll just do this, draw this circle. That's the symbol of voltmeter, and I'll complete the circuit here. Good, and that's it. This is the voltmeter that is connected to measure the potential difference across the lamp. So we go straight to the next question. The next question says, the student places a sliding contact S on the resistance wire CE as close as possible. Okay, draw a voltmeter connected to measure the potential difference across the lamp. You've done that. The second question, the student places a sliding contact S on the resistance wire CE as close as possible to the point C. Okay, so we look at this is the point C. So this sliding contact was placed at this point. Okay, good. So what's the next thing? Let's see. She measures the potential difference V1 across the lamp L and the current I1 in the circuit. The readings are shown in figure 2.2 and 2.3. Record the readings shown in figure 2.2 and 2.3. Okay, so when you place this sliding contact here, what will be the voltage displayed here and what will be the current displayed here? That is what the question requires of us. So we're going down to these diagrams and we want to read the value here. So if you look at 0, between 0 and 1 we have 5 division, okay? Between 0 and 1 we have 5 division. So if you do 1 divided by 5, this will give us 0.2. That means each smaller division is 0.2 units. Good, so this is 1, this is 2. So we start going through the smaller division. 2.2, okay, 2 plus 0.2 gives us 2.2. 2.2 plus another 0.2 gives us 2.5. 4. So the reading here will be 2.4 volts. Okay, so that is what we are going to write down there, that the voltage is 2.4 volts. So let me just go down there and write the reading on the voltmeter. So you have 2.4 volts. So we do likewise for the current. Okay, we do the same thing for the current. Just try to get what each division represents. Now look at this ammeter. The first reading here is 0. Here we have 0.2, and there are 10 divisions between 0 and 0.2. So to get what each of the smaller division represents, you just do 0.2 divided by 10. You get 0.02. So each of the smaller division represents 0.02 units. Now let's go. Here we have 0.2. We now go to the smaller division: 0.22, 0.24, 0.26, 0.28, 0.3. After 0.3, 0.32. So the answer here will be 0.32. And we put our SI unit in amperes. So our answer is 0.32 amperes. 0.32 amps. Easy, right? Yes, of course, it is easy. Okay, so let me erase all of these because they are not part of the answer. So I'm erasing this from the diagram. Good, so you can focus on the question. Now the next question says, calculate the resistance R1 of the lamp L using the equation R1 equals to V1 over I1. Okay, let's go. If we divide V1 by I1, V1 is the voltage here, which is 2.4, divided by I1, which is the current here, which is 0.32. So you go to your calculator and you do 2.4 divided by 0.32. Get your answer. 2.4 divided by 0.32 gives us 7.5. That means your resistance R1 is 7.5 ohms. Good. The SI unit of resistance is ohms. Question C. She places the sliding contact S on the resistance wire as close as possible to the point D. Point D at the midpoint of the resistance wire. Point D is at the midpoint of the resistance wire. She measures the potential difference V1 across the lamp L. V1, so this is the potential difference she got across the lamp, okay, when the sliding contact is at the point D. What do you mean by the point D? Look at the circuit. This is the point D, midway along the sliding contact, along this along this resistance wire. Okay, good. So if you put this sliding contact at this point, what will be the resistance? Take note that the sliding contact can make contact with any point along this resistance wire, and as you are sliding it from the left to the right side end, the resistance in the circuit will be increasing. Okay, when you put it here, the resistance contributed by the sliding wire is 0. When you bring it here, it is contributing some resistance. When you bring it to the right end, it is contributing maximum resistance to the circuit. So that is what we'll be working on. Okay, good. So let's go back to the question and see what we'll do about that. Now the question says, she measures the potential difference V2 across the lamp L, and the potential difference is 1.4 ohms. Then next, she measures the current I2 in the circuit, and the current I2 is 0.24 amperes. What we should do with these values? The question says, calculate the resistance R2 of the lamp L. Use the equation R2 is V2 over I2. Include the units. Give your answer to suitable number of significant figures for this experiment. So now R2, the formula has already been given to you. So you just divide V2 over I2. What's our V2? Our V2 is the value we have here, which is 1.4 volts. What's our I2? I2 is what we have here, 0.24 amperes. So you just divide 1.4 by 0.24. Whatever you get, that will be your answer. So you go 1.4 divided by 0.24. This gives us 5.83 ohms. So you write it here as 5.83 ohms. That's the resistance we have here. Now, what next does she do? Question D says, she places the sliding contact S on the resistance wire as close as possible to point E. What do you mean by that? Look at the circuit. This is point E. So she places the contact here in order to increase the resistance in the circuit to the maximum value. Okay. So when you place the contacts here, the entire resistance of the sliding wire would add to the circuit. So when resistance is increasing, then current flow in the circuit will reduce. Okay, so let's see if the current will reduce. Let's start by checking the voltage. The questions, okay, so after that, she measures the potential difference V3 across the lamp. This is the resistance. She measures the current I3 in the circuit. This is the current. You can see current keeps on reducing as she's increasing the length or resistance. Now, calculate the resistance R3 of the lamp. Use the equation R3 equals to V3 over I3. Include the SI unit. So what's our V3? 0.9. What's our I3? 0.18. So now you divide 0.9 by 0.18. 0.9 divided by 0.18, that gives us 5. Yeah, so our resistance is 5 ohms. Good. Easy, right? Of course it is easy. Now, question E. Complete the following statement referring to your practical experience and the result. Question 1. As the length of the resistance wire included in the circuit is increased, the brightness of the lamp. Okay, now the question is on the brightness of the lamp. Now, how do you know whether the brightness of the lamp is increasing or reducing? The brightness of the lamp increases when the current is increasing. The brightness of the lamp reduces when the current is reduces. Why? The current determines the brightness of the lamp, the current flowing in the circuit. Now let's come and investigate the trend of the current. Current I1 is 0.32 amperes. Now as she increases the length, as she slides this, what happens to the current? The current reduces to 0.24. And then when she kept on sliding it, the current reduced again to 0.18 amperes. Now let's investigate. Now look at this. Now, how would you comment about the brightness of the lamp? What happens to the brightness of the lamp? You know, it's obvious that since the current is reducing, then you say the brightness of the lamp is reducing. The brightness of the lamp reduces. That's all. Easy, right? Of course it is easy. So as the length of the wire included in the circuit is increased, the brightness of the lamp reduces. Okay, so I don't have to put all of this. I'll just put reduces here. So once I put reduces here, then the question has been answered. The next question, as the length of the resistance wire included in the circuit is increased, the resistance of the lamp, what happens to the resistance of the lamp? Is it increasing or reducing? Let's go back and investigate resistance. In the first case, our resistance was 7.5 ohms. Then this resistance reduced to 8.3 ohms. Then resistance reduced to 5.83 ohms rather. Okay, that's R2. Then the resistance reduced to 5 ohms. So that simply means the resistance of the lamp also reduces. Okay. No, of course, that must be because the lamp is not an ohmic conductor. So when current is reducing, the resistance of that lamp reduces since it is not an ohmic conductor. Question 5. Question F. A variable resistor can be used in this type of experiment in place of the resistance wire. Draw a circuit diagram to show a variable resistor in place of the resistance wire. Include ammeter and the voltmeter in your diagram. So I will draw, the next thing you see is the diagram. So this is the circuits that we have. All the components have been included. So we have to include the voltmeter, and then we have to consider the appearance of the original circuit, and in why we replace the the resistance wire with the variable resistor. So you can see after the voltmeter in parallel with the lamp, then we have the resistance wire here. After the resistance wire, the next thing that comes in is your what? Is this sliding wire making contact with the resistance wire. So you have to put that here, and right here we put the resistance. So you are replacing it with a variable resistor. So you draw the symbol of a variable resistor here. A variable resistor will have an arrow here to show that you can vary the magnitude, you can vary the value of the resistance. So all your connecting wires must be properly drawn. Your connecting wires must make contact. Your circuit must be closed. There must be no open circuit at any point. The only open circuit that is allowed here is the switch, which is up there already. And then your voltmeter will be connected to this point, and then you have a wire running through, and that is it. You must ensure you don't have any open circuit. Does this look good? Let me zoom in and fix all of this. So you have to use correct correct everything must be correct. So I'll fix this like this, I'll fix this like this, yeah, and then I'll complete this symbol of the lamp. This is the lamp. Good. So this looks good enough. And that's it. That's all we have. This is settled, right? Yeah, this is settled. So let's go to the next part of the question. Let's see what we have if we have a satisfactory result. Okay, so the circuit looks very incomplete. Let me complete it. Good. So that's it. This is what you have. Ensure you just do a perfect diagram, okay? Don't have this shading I'm doing here should not exist in your work. Let me just do a perfect job once and for all. So it's because I'm no longer zooming in. That's why I'm making these mistakes. Okay, so this is done. This is perfect. And that's all. So this is the end of this part of this work. Let's go straight to the next question. Question number 3 that has to do with heat. Let's go. Now we go straight to question 3. A student investigates the effect of the starting temperature on the cooling rate of water. Figure 3.1 shows the apparatus. So this is the apparatus. We have the beaker, we have a thermometer, we have a retort stand and a clamp. Okay, this is the bench. Okay, so the experiment was carried out on a bench. Question A, the A part of the question, it says, the thermometer in figure 3.2 shows the room temperature, theta R, at the beginning of the experiment. Record theta R. So let us read the value we have here. Okay, so the calibration here shows the reading. Okay, so start from -10, 0, 10, 20. So we have 10 division for each 10 units. So each of the smaller division is 1 unit. So this will be 21, 22, 23. That's it. 23 degrees Celsius. So we put that in the space provided for temperature, 23 degrees Celsius. Theta R, we write 23 degrees Celsius. Good. Let's go ahead with the next question. The next question says, the student uses a measuring cylinder to pour 200 cm cube of hot water into the beaker. He records in table 3.1 the temperature theta of the hot water at T equals to 0. He measures and records in table 3.1 the water temperatures every 30 seconds. Complete the time t colon in table 3.1. Take note that he does that every 30 seconds, right? Starting from the time t equals to 0 second. Now let's look at our table 3.1. Okay, the time t equals to 0. Since it's every 30 seconds, that means okay, so when time is 30, let me zoom in so my handwriting will be better. So our time, we put 30 here. Since it's every 30 seconds, we put 30 here. Well, for let us check the SI unit that is written at the top of the time axis. It's in seconds. Good. So we write 30. The next value will be 30 plus 30, which is 60. The next value will be 60 plus 30, which is 90. And then the last value will be 90 plus 30, which is 120. 120. Okay. So after 120, then the last value will be 120 plus 30, which is 150 seconds. Good. So that is our time axis. That is settled, right? Okay, so the next part of the question. Oh, sorry. There's one more. After 150, 150 plus 30, that will give us 180 seconds. Okay, good. So that is settled. Let's go straight to the next part of the question. The next part of the question is on the next page, and it says, calculate the decrease in temperature, delta theta 1, between T equals to 0 and T equals to 180 seconds. So let us see our change in temperature between 0 and 180 seconds. So what we have here, let us use this color to highlight. This is the value when, hold on please. Decrease in temperature between time t equals to 0 and t equals to 180 seconds. So when our time is 0 seconds, our temperature was 88 degrees Celsius. When our time is 180 seconds, our temperature is 87 degrees Celsius. So how do you calculate change in theta? Change in theta, change in temperature is equals to theta 2 minus theta 1. This is the formula we use to calculate our change in temperature. So this is the formula for change in temperature. But because the question specifically asks you to calculate the decrease in temperature, if you are calculating decrease in temperature, then the formula becomes theta 1 minus theta 2. Okay, so that's what we're going to be doing here. We are going to express our decrease in temperature as theta 1 minus theta 2. Okay, what's our theta 1? Our theta 1 is the initial temperature, which is 88. Okay, sorry, theta 1 minus theta 2. Yeah, so our initial temperature is 88 minus our final temperature is 67. 88 minus 67, that will give you 21 degrees Celsius. That give you 21 degrees Celsius. So I'll put that here, 21 degrees Celsius. The next question says, calculate the average rate of cooling of water using the equation rate of cooling equals to change in temperature divided by change in time, where change in time is 180 seconds. Yes, the change in time is 180 seconds because yeah, we pick our change in temperature from here to here. Okay, therefore our change in time will always be within that range. Okay, take the difference, 180 minus 0 gives us 180. So you divide our change in temperature, which is 21, divided by our change in time, which is 180, and our answer will be 21 divided by 180. 21 divided by 180 gives us 0.12 or 0.117. I think, yeah, 0.117 is better. 0.17 for more accuracy. So our cooling rate will be 0.117. Change in temperature divided by change in time. Temperature is measured in degrees Celsius. So you have degrees Celsius per Change in time is measured in second. That's degrees Celsius per second. So your answer and the SI unit. Perfect. Question D. The student empties the beaker. He pours warm water into the same beaker. He records in table 3.2 the temperature of warm water at T equals to 0. He measures and records in table 3.2 the water temperature every 30 seconds. So every 30 seconds, he measures the temperature. These are the temperatures. Using table 3.2, calculate the decrease in temperature, change in theta 2. We are using theta 2 because we are dealing with the second situation where we are using warm water of 72 degrees Celsius. Calculate the change in temperature between T equals to 0 and T equals to 90. So from T equal to 0 till T equal to 90, let us get a decrease in temperature rather. So when you want to get the decrease in temperature, you use theta 1 minus, you use the temperature is theta 2, right? Good. So theta 2, the first case of theta 2, let's call it A, the first case of theta 2 minus the second case of theta 2. So I'm using A and B. A is the initial temperature and B is final temperature. The initial temperature is 74, okay, which is what we have in the beginning, and the final temperature is 68. That will be 74 minus 68. And the answer will be 6 degrees Celsius. Perfect. Yeah, that's 6 degrees Celsius. Let me just do a perfect job here. So you have 6 degrees Celsius. Good. The next question says, let me finish this. Good. The next question says, calculate the average rate of cooling of water using the equation change in theta 2 divided by change in time. Your change in time is 90 seconds. Take note that the change in temperature is from here to here. Also, your change in time should be here to here, which is 90. So we'll divide our change in temperature, which is 6. Our change in time is 90. 6 divided by 90 should give us 2 over 3. That's 0.0667. Let me confirm. 6 divided by 90. 6 divided by 90. That should be 0.0667. Good. So you have 0.0667 is enough. 0.067. Temperature is measured in degrees Celsius. That will be Celsius per, time is measured in second. Celsius, degrees Celsius per second. Good. Now the next question says, a student suggests that the rate of cooling of water depends on the initial temperature. Okay, take note of the rate of cooling in the second case, where the initial temperature here is 74. So when the initial temperature is 74, the rate of cooling is 0.067. And when the initial temperature was 88, the rate of cooling was 0.117. You know, 0.117 is bigger than 0.067, right? Good. Now the question says, a student suggests that the rate of cooling of water depends on the initial temperature of water. Write a conclusion about the effect of the initial temperature of water on the rate of cooling of water. Based on the result, justify your conclusion by reference to values from the result. Okay, so write about the effects of initial temperature on the cooling rate of water. So what's the effect of the initial temperature on the cooling rate of water? So this is our conclusion that the higher the initial temperature of water, the higher its cooling rate. Or you say water at high temperatures cool faster than water at lower temperatures. The question then proceeded to say, justify your conclusion by reference to values from the result. What are the values from the result? What value from the result show us that this conclusion is justified? Now these are the values. When the initial temperature was 88 degrees Celsius, what was the cooling rate? The cooling rate was 0.117. So you just put that down here, okay? That when the initial temperature was 88 degrees Celsius, the cooling rate was 0.117. So that is it. That is how you state the justification for your answer, okay? When the initial temperature was 88 degrees Celsius, the cooling rate was 0.117 degrees Celsius per second. While when the initial temperature was 74 degrees Celsius, 74 degrees Celsius, okay, the cooling rate was 74 degrees Celsius. So you put 74 here, this should be 74. The cooling rate was 0.067 degrees Celsius per second. The last part of the question, the next part of the question states two requirements when reading the volume of water in measuring, states two requirements when reading the volume of water in a measuring cylinder in order to obtain accurate results. Whenever you are reading a measuring cylinder, number one, you must read the bottom of the meniscus, okay? The curve would have this shape, okay? So you have to check the bottom of that line, okay? The second precaution is that your eyes must be at the same horizontal level with the mark, with the level of water in the cylinder, okay? It must be at the same horizontal level with the bottom of the meniscus. Those are the two requirements, okay? Once you do that, you will not record apparent volume, and you also avoid parallax error. So those are the two precautions. What do you mean when we say the same horizontal level? This is what we mean. Your eyes must be at the same horizontal level as the meniscus. This is what I mean by meniscus. This curved shape that water forms when placed in narrow bottles, okay, in narrow capillary tubes. So this is the shape. Also in narrow test tube measuring cylinder, water forms this shape. Also take the reading at the bottom of the meniscus. This is the bottom of the meniscus. So your reading must be taken from this bottom level, okay? From this bottom of the meniscus. That's where you take your reading from. If you take your reading from the top, you'll be reading the apparent volume, okay, the fake volume. But when you read it from the bottom, you will read the actual volume of water in this tube, okay? When you from the top, take note that all of these spaces are not filled with water, okay? So you'll be taking the fake volume of the water. It's clear, right? Good. Now the next question says, suggest two possible variables that should be kept constant. Those are the two variables that must be kept constant. The volume of water used in the two experiments, also the time interval or the duration of the experiment. Why? Because in practical setting, temperature in Celsius, in practical setting, time in seconds. The cooling curve of water looks like this. What does that mean? That means at high temperatures, water cools at a very fast rate. That's why the curve looks like this. It cools at a fast rate. But at lower temperature, the cooling rate looks like this. And at room temperature, the cooling rate is just like this. That means the temperature is constant. The water does not cool. So if you are coming from high temperature, the cooling rate, that's the slope, is high. The cooling rate is high. Okay, good. So that is why you have to ensure the time interval, ensure equal time interval. If you don't use equal time intervals, you will not get you won't be able to compare your values here. So time intervals here are equal, but in a situation like this, the time intervals here are not equal. So you won't be able to see the actual slope in the experiment. Okay, good. So that is it. That is how you get that done. I think this brings us to the end of this question 2. Question 3, now we are going straight to question 4, which involves that checks your ability to plan an experiment. Yeah, so now we are going to question 4. Question 4. Question 4. A student investigates the horizontal distance traveled by a metal ball after it rolls off the end of a plastic track. This is the plastic track. So we have a metal ball at this end of this plastic track. and the metal block will be made to roll down this plastic track. Okay, and then at this point the metal block will jump off this track and follow this parabolic path. Okay, it will follow this parabolic path. Okay, so and it will land here. But how do you get to know the particular point it lands? The best way to do that is by placing a sand tray here. So you place a tray here, fill that tray with sand. Yes, so that way you get to know the exact point where the ball lands. Okay, so let's assume the ball lands here and creates an indentation in the sand here. Then you place your meter rule here to measure this distance accurately. Good. So that's the procedure. That is how you get accurate result. This is your meter rule to measure the distance. Okay. Take note that you must measure the distance from this point where this ball leaves contact with where it leaves the track. Okay. So from this point here, so it's better you have a meter rule. Use your meter rule here. Just you can mark a point here on the floor. Okay, so once you get this point, by placing your meter rule vertically, okay, you can use a plumb line, attach a plumb line to your meter rule in order to get it standing perfectly straight. Okay, then you place a meter rule here. Okay, from this line you mark on the ground to wherever the ball hits the sand tray. Okay, good. So that's how you get your accurate measurement of the distance traveled. Okay, then you need a protractor here. Use a protractor to read your angle. So when you are listing the apparatus, you can add a protractor that you put here to measure this angle to it. So that is the procedure we'll be taking in carrying out this experiment. So that's what we do to ensure accurate results. Good. So you may just add the sand tray to your diagram to ensure you do a perfect job. Now we proceed with the procedure. Let's go. So let's go straight to the first question. The first question says, the following apparatus is available to the student. You have a track with sand, then balls and clamp. Okay, so you may have a track with sand. Okay, instead of placing a sand tray here, the track itself, sorry, track with sand. Okay, good. So this is the track, this is the sand. Okay, this is the sand tray, please. Then this is the track itself. This is the track, this is sand. The sand will be poured into the sand tray, okay, so that you can accurately get the location, the point where the ball lands on the tray. Then selection of metal balls. Okay, you have so many metal balls, but the advice you use one metal ball so that you ensure the mass that is sliding down this track is constant. Okay, if you use different metal balls, then you end up getting different values. All right, I don't want to have the answer yet, just the question. Question one. Okay, other apparatus normally available in a school laboratory can also be used in your plan. You should, number one, list any additional apparatus required. So this question is guiding you in the process. So what additional apparatus would you require? So you put them here, other apparatus you require. You need a meter rule to measure the sand tray, to measure the distance rather. Then you need a sand tray filled with sand to measure what? To get the exact location where the ball lands. You also need a protractor in order to measure the angle that in order to measure the angle that this right hand side of the track is making with the table or with the bench. Yes, so you measure the angle here. You can call this angle here theta. Yes, we can call this angle theta just to make it easier to identify different parts of this diagram. We can call this angle theta, then the distance traveled is the distance d. Yes, so these symbols will be used in our table. You know, every physics experiment, you might have to create a table along the line. Okay, so after listing, then the next thing is to explain briefly how you will do the investigation. including the measurements you would take. So how will you do this investigation? Okay, so we should write that here. Let's go. So I've explained the procedure, increase the vary the angle, then after varying the angle, allow the ball to slide and you measure the distance, then you tabulate your result. So this is the procedure. Step one, you adjust the angle theta. So let me put theta here. Adjust the angle theta. Okay. You adjust the angle theta on the right hand side of the track to be 0 degrees. So you are starting with angle 0 degrees. After that, you place the ball on the leftmost end of the track and release it for it to roll down. Yeah, so for it to roll down the track. Then you measure and record the distance d traveled by the ball during its flight. So when you release the ball here, the ball will roll down. Then once it leaves this point, then it will fly and land wherever at any point. So wherever it lands, you now measure the distance. So that's why I put d here as the distance from the beginning, that's where the ball takes off, to wherever the ball lands. This distance here, you label it d. Good. So let's proceed. The next step says, okay, so now you measure and record the distance d traveled by the ball during its flight. Okay. Also, you record the value of the angle theta. You measure your angle theta in degrees Celsius. Okay, and the distance d in meters traveled by the ball during its flight. Good. So you may just add that here, that your distance d must be measured in meters and the distance d in meters. Let me remove this. And the distance d in meters traveled. Okay, so this is good enough. What's next? Repeat the procedure for 4 other values of angle what? Angle theta. So you now repeat the procedure when theta is equal to 10 degrees, 20 degrees, 30 degrees, and 40 degrees. So you vary this angle on the right hand side. You're starting with 0. That's when this when the track was, the right hand side was completely flat. Okay, that's the first angle. Then you raise it a bit to be 10, you raise it to 20, 30, and 40. And each of these angle, you repeat the procedure. You measure the distance traveled during the flight. So the next thing you do, state the key variables to be kept constant. So what are the variables you keep constant? Number one is the mass of this ball. The mass of the ball must be kept constant. Okay. So apart from the mass of the ball, what else will you keep constant? You avoid the air. You avoid wind. Yeah, wind can be blowing this ball and be acting against it. Okay. When you have the wind acting in this direction, then it will be reducing the speed, okay, and that can reduce the distance, okay. If in the second procedure the wind is acting in this direction, then it will give undue advantage to the movement of the ball. So you just avoid wind completely in order to get perfectly accurate results during the experiment. So I've listed that during the experiment the following values must be kept constant. Number one, the same ball must be used throughout the experiment, okay. Good. Or you use a ball, yes. So when you use the same ball, then the mass will not vary. Also, there must be no drought or wind throughout the experiment. Then the experiment must be the location of the experiment, or you say the experiment must be carried out in one location. Why would you do that? To ensure that the mass does not change. Okay. Why? Because to ensure the gravity does not change. Okay. Yeah, since gravity varies from place to place. So if you want to have one value of gravity, then you carry out the experiment in one location, okay? Because once they are moving, then gravity, you are experiencing different values of acceleration due to gravity. And that can affect the accuracy of your experiment because you want the force to be constant. When gravity is changing, then the force or the weight is changing. Then the next thing you are doing is what? The next thing you are doing is to do what? Is to draw. The next question says, Draw a suitable table with column headings to show how you will display your readings. You are not required to enter any readings in this table. So what are the headings you use for the columns? What column headings will you use in this experiment? Okay, take note that the first thing you have to measure is the angle theta, right? Good. So you are using different values of angle, then you measure the distance. So the first thing you have is your angle theta, and you put your unit there. The units must be in degrees Celsius. After that, what else can you do? You can add other values to it. Actually, the two most important values are your angle theta and your distance in meter. That's all. Or you use your distance in centimeter, whichever one you are using. Your angle in degrees, then your distance in meters. Okay, good. So any other modification you are making in order to get probably a straight line graph, or you want to get a curve graph, this might give you a curve graph. And if you are using sine theta, okay, if you are adding other analysis by using sine theta, or you decide to use sine 2 theta for instance, okay, so this might be done probably in order to get a straight line graph. Okay, remember from the equation of projectile motion, r equals to u squared sin 2 theta all over g. U squared sin 2 theta over g. Yes, so you might decide to include this sin 2 theta and even this u squared. How will you vary u squared? You know, you cannot alter the initial speed. So all of these are not actually necessary. The two most important things are just the angle in degrees Celsius and your distance in meter. That's all. What else? The next thing, explain how you would use the results of each, sorry, how you use the results to reach a conclusion. So how you use these results to reach a conclusion? The first thing you do, you have to plot a graph. Okay, so from your table, you plot a graph of angle theta, plot a graph of angle theta in degrees Celsius against distance in meter. So now you determine the slope of the graph. Yeah, so when you plot a graph and you determine the slope of the graph, what can you get from there? A positive slope shows that the distance traveled by the ball increases as the angle of inclination of the right hand side of the track increases. A negative slope shows that the distance traveled by the ball decreases as the angle of inclination of the right hand side of the track increases. Sorry, let me fix this. So a negative slope shows that the angle of inclination would would not make the distance traveled increase. So a negative slope shows that the distance traveled by the ball decreases as the angle of inclination of the right hand side of the track increases. If the slope is zero, then there's no relationship between angle and the distance traveled by the ball. What does this mean? That means when you plot your graph and a graph of angle theta in degrees Celsius against the distance in meter, if your slope looks like this is a positive slope. It shows that distance is proportional to angle, that is proportional to angle. If your slope looks like this, then distance is inversely proportional to angle. That means as angle increases, distance decreases. If your slope is just a horizontal line, that means the angle does not have any effect on the distance, okay? So that is how you come across your that's how you arrive at your conclusion. Okay, but it's very likely you get a slope that looks like this. Okay, what you can have is a curved slope looking like this. Okay, yeah, and this is also it also has a positive slope. Okay, good, and it also shows that distance is proportional to the angle of inclination of the right hand side of the track. This brings us to the end of paper 6 of 2022 October-November IGCSE examination. Ensure you subscribe to this channel and come back to watch more videos. Do have a nice day. See you on the next series. Goodbye.